Oh my God, Taylor.
Hi everyone. Okay, bye everyone. Mr. Lenfestey, you're gonna have my little brother next to you. That's gonna be a treat.
Taylor, is that a new couch?
The green screen, buddy.
Oh my God.
Dude, Kevin, put your screen on. Look, speak of full screen.
So Aiden, you still have your internship going on?
No, I told them I had corona, so I could be here.
Oh, Kenzie.
So I'm
Kenzie,
here,
what's
Mr.
up?
Lenfestey. I told them I have a slight cough.
Oh.
So they said, you can stay home today. So I'm here.
All right. Well, I think we're going to go ahead and get started. So first of all, at the end of the meeting, I'll be able to let some of you know whether you have to do the SWIC or not. I won't be able to let everybody know because I know some people have just emailed me some of their whiteboards at the last second. So, but regardless, whether you have to do the SWIC or not, don't think of it as a penalty because it's not really that hard. It's like just an attendance thing. I need to keep track of attendance to let the administration know that everybody's here. So that way, there's a couple different ways you can do it. You can participate during the meeting. Hopefully, that's all taken care of, and I'll let you know at the very end of the meeting that you don't have to worry about it. For the people who are not able to attend to it, or I wasn't able to look at their whiteboards quick enough, then you can go ahead and do the SWIC. It won't take that long, probably 10 minutes at the most. Anyway, so I thought first thing I probably ought to talk about is where we are with the actual AP test. So there's going to be a couple different dates. I don't think they've been chosen yet when the AP test is going to be. It won't be multiple choice at all. It's going to be a free response. The truth is we've covered everything already that they're going to do because they're cutting magnetism totally out of it. So, there's a couple different options. There's an option where we can just go ahead and start reviewing for the AP test. I don't really want to do that because I kind of feel like you're ready for it already. I mean, if you're doing the internet homeworks and stuff, I mean, we've already done circuitry. We're still reviewing that on the AP homeworks or internet homeworks, the electrostatics, which we kind of really hit that over and over again. And I'm kind of tired of it. And I think you are, honestly. So I'd rather not just start reviewing that. However, I am going to open up what's it called? The AP classroom. I really haven't done it because I don't really like that much. It's kind of a beta version thing. But that way, if some people want to go ahead and start practicing, I think you're kind of ready for it already. I'm kind of a little bit worried about the test, though, because it's going to be online, free response online. And so I'm kind of worried about that, of how that's going to be exactly. Not that I'm worried about your abilities. I'm just kind of worried about, what's the interface going to look like and how hard is it going to be to type in your work and everything. So I don't really understand how that's going to happen. Second of all, I really don't want to just start reviewing right now because I really feel like for those still planning on going to engineering or into physics or something like that, I think you're kind of being shortchanged if we do that because first of all, I think this next unit with magnetism isn't that hard. I also think it's kind of interesting. It's kind of unfortunate we're not in the classroom to see it, but I'm going to do the best I can to make videos and this Zoom thing work where I can do demos and stuff. But I think it better prepares you for college too. So, but if 2/3 of you want me to go ahead and start reviewing, so you need to send me an email saying, hey, yeah, I want to start reviewing, then I will go ahead with what you say, but it's a quorum. It's got to be 2/3. I want 2/3 of you to say, yeah, that's what we need to do, or it's not happening. We're going to keep on doing magnetism stuff. Does that make sense? Okay, all right. That's what I know about what's going on with the AP test then. Okay, so let's see, we're going to start whiteboarding then the lab. And the Slinky Lab, really what I wanted to look at was your graphical and mathematical models for this. And the purpose that I sent you, I think, in the handout thing was to graphically and mathematically model the relationship between the magnetic field and those three things: the current between the magnetic field and the length of the slinky, and then the magnetic field and the number of loops that were in that slinky thing. So I just kind of want to look at the data that I shared with everybody, because unfortunately we had to just go with the data that I got. And so the data kind of look like this. Let's see, rotate. So we all had the exact same data, so we really should all get the same relationships, right? Yeah. Okay. So I do want to point out here that I'm hoping that nobody used this data right here where I crossed out, and I kind of put my reasons why that shouldn't be used. Same thing for this one here. I put my reason, and the last one was fine. Also, I'm kind of hoping that you you converted those to Tesla, although it's not too important, I guess. I'm pretty sure that we all graphed it, hopefully, where the magnetic field was the dependent variable, kind of like I have it set up here. The last thing is, before we start looking at whiteboards, since we all should be the same, and we don't know what the answer is, what are some ways that we know, you know, when you're trying to figure out, do I need to linearize or not, what are the things you look at that help you figure out if it should be linearized?
The graph.
I'm sorry, you cut out.
The graph.
Okay, what about the graphs though?
Is it linear or not?
Y-intercept.
R-squared value.
Okay, the R-squared value, the y-intercept, and do you guys remember from last year, sometimes the slope too, like the units of the slope. So those three things. Okay, so you're looking at the R-squared value, so you're always trying to get a 0.98 or better, or 0.998 or better. But at the same time, you have to weigh that with looking at the y-intercept. Does it make sense to have a y-intercept or not? And then sometimes you kind of want to look at the units of the slope. Okay, so just having that in mind. All right, so let's see here. Oh, before I go any further, just in case you guys have to do this quick, let me give you some of the letters in the code, the digits of the code. This is a 9-digit code.
So
The first 3 digits, these are all capital letters, so you should write this down. You should write this down just in case you have to do the SWIC. The first 3 letters are all capitals: W-E-D. W-E-D. Could you also type into this Zoom meeting your first and last name? So you're given and surname, please, for attendance purposes. Thanks. Okay, so I'm going to actually look at everybody's whiteboard here. So I think I'm just gonna, all the ones I have here, and then I'll also check email here in a second. For some reason, it wasn't letting me click on these in the other whiteboard meetings I had. So I'm just going to copy and paste. So it looks like Mark, Joe, and Aiden had for the current the B field versus current, looks like it was a direct relationship. Yep. For the magnetic field versus the length, it looks like it was an inverse relationship. And for the magnetic field and the number of coils, it looks like it was an inverse relationship. So direct, inverse, inverse. Okay. All right. So then let me look at the next group. This ought to be fun. Since we all had the same data, we should all get the same relationships. Let's see if that's true.
Oh God.
All right. So this is Riley's stuff. Let's see. I think it is this one here. Okay, so they also got a direct relationship for versus current. For the length, they had also an inverse relationship, but for the number of coils, they actually had a direct relationship. So that's interesting compared to the last group. Let's see. All right, so let's get rid of that one. And then let's get the next one here. This is Matt and Kevin's.
Kobe, did you share it?
Yeah.
Okay, so for the magnetic field versus current, also they got a direct relationship. For the magnetic field versus the length, it kind of looks like it's linear already, although it's kind of going down, which we've never seen. So perhaps that might be inverse. So I think Matt and Kevin, I might ask you to see if maybe that might be an inverse relationship. And then for the B field versus the number of loops, it kind of looks like they have a side opening. Okay. All right, and let's see the next group. This might take longer than I thought. Okay. And let's see. Matthews, Miranda's, and Kylan's, they said versus the current, it was a direct relationship. Versus length, it looks like it's inverse at first, but then it must have been kind of a side opening. So they did B squared versus 1 over L. Okay, and then they had a direct relation. No, that's not true. It looks like maybe it's a side opening versus the number of loops. So kind of like the last group, I believe. So B squared versus N. Okay. All right. And let's see another group here. Kayla and Kenzie's. Let's see.
Okay, Kenzie.
Okay, it looks like it's direct relationship for the first one. So it looks like we all agree so far for that. It looks sort of like it was inverse, but no, it looks like actually after it was inverse, they had to plot B squared versus 1 over L. And then for the last one, it kind of looks like it is a side open relationship. Okay, so I think we had 3 groups that said that. Is that it? That's it from there. Okay, so let me close that out and let me check my email. Okay. Okay, looks like they also agree that it's a direct relationship. For this one, it kind of looks like it's a direct relationship, but it's going down. So therefore, maybe that might be an inverse relationship. So Matt, Adam, and Adam, maybe I would like to suggest that maybe it might be inverse. So why don't you check that one out? And then it looks like they also kind of agreed that last one is B squared versus N. So going back to the first one here, Mark, Aiden, Joe, you're kind of like you're the odd guys out. So why don't you check that one out again? All right, we'll come back to you. Then let me check your
What?
Switch the axes on one of them.
Kobe.
Try to do
Sounds like Mark's getting chewed out. It
I got the
looks
line,
like
Kobe.
it looks like for the current, it looks like a direct relationship here again. This group, Kobe says that. It looks like they said inverse relationship for B versus L. And then for the last one, it looks like they had a linear relationship, so not direct necessarily. Okay, so all right. And then let's see.
I think I just put X and Y. Because like it's good. Yeah.
Okay, so for this one, it looks like they had a direct relationship. For the next one, it looks like, again, they said it was linear, but it was negative slope. So I'd like to suggest that maybe it's inverse or some kind of inverse relationship. And then for the last one, it looks like they plot N versus B, but it really should be B versus N. So it looks like they have a direct relationship too. So I think that's all the groups that I had share anyway. Did I miss anybody? All right, so it looks like everybody agreed that the first relationship, oh, by the way, I just now saw this, it should be B versus I. This one here should be L versus, or excuse me, B versus L. But it looks like everybody agreed that the first relationship is a direct relationship. It looks like we have a little bit of controversy about the second one, whether it's B versus 1 over L, or a lot of groups are saying B squared versus 1 over L. And for the last one, it looks like most groups are saying it's B squared versus N. And we have a couple groups that are saying B versus N. Okay, so I'm going to put those away for a second, and I'm going to show you my data, which is the same data as your data. So that's interesting. So I agreed with everybody else that for the very first one, it is a direct relationship. And the reason why I say that is because the y-intercept, which is 7 times 10 to the -6, the biggest magnetic field is, it kind of looks like that first one there. So I'm going to take that first one and multiply by 0.05. And clearly that number there, which is 1 times 10 to the -5th, is much bigger than the y-intercept. So that is a direct relationship. So we're all in agreement there. Okay. So now let's look at the next one. I don't know, can you guys see this, or is this on? Let me see if I can figure out how to get rid of that. There we go. Okay. So I plotted first, this first one here, I plotted the B versus the length. And I kind of got this downward graph, kind of like the other people got. But there's only certain types of relationships this could be. It could be top opening. Nope, that's not it. Could be side opening. Nope, that's not it. Could be linear or direct. That's not it. So maybe it's inverse. And so that's what I tried to plot right here in the second one, B versus 1 over L. It does kind of look like it might be side opening now. But before we move on, we have to look at two things. We have to look at the correlation, which is pathetic. It's 0.9283. Oh my gosh, Mr. Lenfestey needed some help. But we also need to look at the intercept. The intercept is 9 times 10 to the -6. So 5% of the maximum B for this one was, let's see, it was this value here. And so when I figured that out, I got 4.9 times 10 to the -6. Well, clearly this number is bigger. The y-intercept is bigger than that, but it's only 9%. Clearly, Mr. Lenfestey needed some help, but 9% is not so bad, comes with slack. If you plot B squared versus 1 over L, it does look a lot more linear, but look at that correlation. It's not that much better. It's 0.9521. Let's look at the y-intercept. It's 4 times 10 to the -9th. So for this one, looking at the maximum B squared value, figuring out 5% of that, I get 4.97 times 10 to the -10th. That y-intercept for that last relationship is much bigger than 5%. In fact, it's 40%. So I want you to think about this. For this coil, what that means is that when 1 over the length goes to 0, that means a huge coil. I'm hoping that you would see that when that goes really big for that coil when all the other variables are held constant, I'm hoping you would see that the B field, whether it's B field or B field squared, would go to 0. Well, this says that it's not 0, and that's pretty significant. Where this is still not 0, you're right, but maybe it's due to something that Mr. Lenfestey did wrong. It's a lot closer to being within margin. So the reason why I point that out to you guys is I'm asking you, is it okay to go ahead and just simply go with B versus 1 over L? Are you guys good with that?
Yeah.
Okay, all right. So now let's talk about the last one, the B versus N. So the very first one I got was this relationship, and the correlation is 0.962, still not that great. And the y-intercept is 1 times 10 to the negative fifth. So figuring out what the maximum B field was, it was this first one here, 0.000289. 5% of that is about 1.4 times 10 to the negative fifth. Well, my y-intercept is actually less than that. So I could actually drop it off. It actually is a direct model. Okay. It does though, if you look at it, it does kind of look like maybe side opening though. So I tried to also do B squared versus N. Let me pull this up here. And the y-intercept, or excuse me, the correlation didn't change much. So it didn't get much better, although it kind of looks a little bit better maybe. But then looking at the y-intercept, we have 4 times 10 to the negative 8th. So now 5% of the maximum B squared value, well, that's this top one here. 5% of that is 4.2 times 10 to the negative 9th. Well, this y-intercept that I found in my graph here, that's statistically significant. It's 48% of that value, or 48% of the maximum, should say. So we could not drop it off. And again, what this would say is, think about that coil again. If the number of loops goes to 0, I'm hoping that you say, yeah, the B field should go to 0, or the B field square should go to 0. So I don't think that it's B squared versus N. I think it's more the B versus N.
Yeah.
So are we all good with that? Yeah, okay. All right, so the 3 relationships I think we have is a direct relationship, an inverse relationship, and another direct relationship. All right, so let's go back to that. So actually, could you guys, well, this might be difficult. Could you guys go ahead and force yours to be direct, inverse, and direct? By the way, I need to give you the next 3 letters for the code, so write these down somewhere. Again, these are all capital letters. It's S, W, T. Again, those are S, W, T. Could you again, for attendance purposes, could you again type in your name into the chat, both your first name and last name? Thanks.
Kobe, we're too good.
Well, the only thing though, really, you shouldn't have had a y-intercept.
Oh yeah, true.
No, Kobe did the work there.
Yeah, okay, buddy.
Okay. All right.
Kobe's was wrong at first. I had to change it.
All right. I think I'm going to drop these out. How am I doing on time? Oh, I'm doing fine on time. All right. So, I wonder if I can move this somewhere else. This is in my way. Yeah, get rid of that page. I think I'm going to go on to the models. And I think I'm just going to go ahead and start writing the model. It looks like the joint model is going to be the magnetic field B is directly related to the current I. It's also directly related to the number of loops. So I'm going to call that little n. So n times I. And it's inversely related to the length. But there could be some constant of variation out front, k. So I want you to understand that all the equations that you found are correct, assuming you did it in Tesla and everything like that. And you've forced them to be direct, inverse, and direct. That first one would be the slope that you found. I'm going to call that slope 1, would be equal to, well, if you look at that equation, there's an I in it, but there's nothing else. So it must be equal to K times N divided by L, where N was the number of loops that was held constant, which I think was 179. And the length was also constant, which was 1.218. So here in a second, what I'd like you to do is calculate what that K value is. But before we do that, that second equation is also the same as this equation. So I'm going to call this slope 2. So slope 2 in that second equation. And again, I see a 1 over L, but I don't see the other stuff there. So that means that that slope 2 must be equal to K times N times I. And then finally, that third equation is the same as the equation for the joint model. I'm going to call this slope 3. For that one, I see the N, but I don't see the rest. So that means that the slope must be equal to K times I, times I over L. So what I'd like you to do is calculate your 3 K values. How should they compare, by the way? Yeah, they should be the same, right? Assuming Mr. Lenfestey, assuming Mr. Lenfestey did a great job, which maybe he didn't do a great job, but could you please go ahead and calculate those 3 values? Miranda, how did you get my, where'd you get my picture at?
I don't know. It was in my collection.
Oh my gosh. Oh Lord. Is that one of those, what do you call those deep fake videos? What is that? Deep, I forget what you call those videos where they fake them or whatever. Is that a fake picture of me?
No, it's definitely real.
That's real. Okay. Okay, are those 3 values somewhat in the same ballpark? In other words, what I mean by same ballpark is, do they have the same times 10 to the whatever factor?
Mark, I'm blaming this on you.
They can't be like that.
They should have the same times 10 to the whatever factor.
Those are his constants.
Two of them do. One doesn't. One's a couple millions off.
Yeah,
We're just
let me ask you a question. What did you get for a slope for the B versus I graph?
Is that the first one?
Yeah.
5,370.
Yeah. Mark forgot to divide by 1,000, I'm guessing.
No, it's not 5,000. It's not 5
We did
anything.
that, remember?
Yeah, Mark. That was you. I did the second one. Nice try.
Anybody?
When we divided, remember?
Anybody else want to share what they got for their slope of the first graph?
That was Joe
2
who did
times
that
10
one,
to the
actually.
-4th.
Yeah, 2 times 10 to the -4th. We should all get the same number.
Mark, you flipped the axes in that one. That's what it was. And you did that by 1,000. You flipped the axes in the first one.
Yeah, but the third one was wrong too. And
I did the second one and the third one.
I know the third one.
Okay, so does anybody want to share what their slope was for the second linearized graph?
4.75 e negative 5, I think.
That sounds about right. Yeah.
Oh, dang it, Aiden.
Yeah, see, Mark, I do my stuff right. That's him. Please.
What about the last one? What'd you get for the slope of the last one? That should have been easy too.
Something e negative 4th, I think.
No.
I don't know.
1.6 10 to the negative fifth.
Make a check.
I didn't get negative fifth.
Negative 10.
Negative 10th.
No.
Negative 6.
Yes, somebody said negative 6. It was Matt, is that you?
Yeah.
What'd you get? What'd you get?
1.6 times negative 6.
Yeah, about that. Okay, so what do you guys get for your, how about take your 3 values for your K value? They should be about the same. That means they have the same times 10 to the whatever.
Yeah.
What do you get for your average K value?
E to the negative 6th.
Okay, what number did you get?
1.4, 1.4.
Yeah, that's what I got. I got 1.44 times 10 to the negative 6. So, I mean, I use Excel, so maybe it was some rounding there or something. Okay, so before I put that in, though, I want you to think about what the units would be. The letter N up here doesn't have any units, and I would be in amps, and L would be in meters. But of course, B is in Tesla, so that means K must have units of, we have to cancel out the meters and the amps. So it must be units of Tesla times meters, Teslas times meters over amps. So that means my K value, I get on average for K around 1.4 times 10 to the negative 6th. And to get the units to work out in my equation, it would be Tesla times meters over amps. But before I put that down, really, actually, I'm getting to the consensus model. We had something else that was similar to that recently that had to do with something with magnetic fields. You guys remember what that was?
Yeah, mu naught.
Yeah,
Let's
mu naught.
go, baby.
Yeah, I can't get that symbol, so I'm just going to say mu naught. That looks like the coefficient of friction symbol with a subscript 0 or O. And it's called the permeability of free space, is equal to 1.257 times 10 to the negative 6th Tesla times meters over amps. What do you think? Is it the same thing or pretty close anyway? Considering it was Mr. Lenfestey who did it all by himself, which was impossible. Pretty close, right? Yeah, so that's the equation then that we're going to say it is. So I'm going to see if I can write it then. B equals, boy, I'm going to see if I can just draw it here in a second. So it's going to be N times I, and then over L. And let's see if I can draw some stuff here. I'm going to try to scribble it in. Hey, that's not bad. Hey, that's pretty good. So there it is. There's the equation. So mu naught times Ni over L. All right, so any questions about that? That's the equation for this. I think before I go any further, I want you to remember what it was for just a wire. If you just simply had a wire that, let's say we have a wire here in space, the magnetic field around this wire kind of looks like, how am I doing on time? Okay, not too bad. It looks like a circle, or it's circular, I should say. And if you wanted to figure out what that magnetic field is, it kind of looks like this equation a little bit. It's B equals that same mu naught times I over 2 pi r. I'm going to move this over a little bit more. So, I mean, it's similar, not exactly the same. But it's similar. Oops. Oh, come on. Okay. Sorry, not very good at this. The reason I'm kind of taking some pains here is because I'm kind of hoping that it reminds you of back when we were doing electrostatic stuff. We're starting to get lots of different equations. We don't want to have to memorize all these different equations. Sorry about that. It's not exactly very good. Let me move that over a little bit more. There, I think it's a little better now. We don't want to have to memorize all these equations. There must be a better way. And if you remember, what we did in electrostatics was we had this Gauss's law that we always used every time. And that was the closed integral of E dot dA equals the Q enclosed over epsilon naught. Well, we can kind of do the same thing here. It's kind of a Gauss's law for magnetism here. Except what we need to do, instead of enclosing a surface area, with Gauss's law, you enclose a surface area. For this one, it's not a surface area. You're looking at along this path. I try to highlight the path for you. And so it's not, you're not enclosing a volume. You're kind of making a circular shape around this. By the way, there's a cooler name if you're thinking about with Gauss's law. Remember, we always call those Gaussian pillboxes. Yeah, that's not cool. We have a cool name. It kind of reminds me of Star Trek. We call these shapes that we make, we call them Amperian loops. So when we integrate, we're integrating across this Amperian loop. The truth is, we're not really integrating either, because we always know what the distance around this loop is going to be. It's going to be a circle, so it's just 2 pi r. Now it's a little bit different for this one that we're doing here, because it's not a circle. So let me pull this one up. So application. So I'm hoping that you can imagine this. One of the hard things in the magnetism, actually electrostatics too, is you kind of have to be able to visualize three-dimensionally. And so this picture, what we're seeing here, and I'll try to put a circle around it. This thing right here is actually that slinky. It's just I've cut the slinky in half so that you're seeing the wire in different sections. Like the top half up here, it has dots. That's supposed to be the flow of current is coming towards you. And at the bottom half of the slinky down there, that's the current when it goes loops back around and goes into the page away from you. So we're kind of looking at a cross section of the slinky. Well, for this, it doesn't make sense to draw an Amperian loop that does this or anything, because the truth is, in fact, this goes to question number 18 here. It says draw the magnetic field inside the slinky here. Think about, I would like everybody right now to go ahead and use right-hand rule on this and figure out which way, if you're grabbing one of those loops, let me see if I can kind of draw a loop here. So imagine that you had a loop like this three-dimensionally. I hope that you can imagine it, and you're gripping it. You have to grip it such that the top part of it, your thumb is pointing toward you, your right thumb. And at the bottom, your thumb is pointing away from you. It's not so much about your thumb. The thumb helps you figure out how to grab it. It's all about your fingers. So which way inside of here will it point? So think about it for a second.
The inside will point to the right one.
Okay, so let's see. You grab it like this, so it points at the top. It's definitely pointing to the right. Let's see if at the bottom is also pointing to the right, isn't it? Can you see that? So whether you grab the top here, pointing to the right, or if you grab the bottom, it also points to the right. So in other words, if I asked you to draw in the magnetic field here, it's always going to be pointing this way.
Oh, Lordy.
Does that make sense? Any questions on that? Okay, so given that the magnetic field is like that, it doesn't make sense to draw in the magnetic loop all the way in here, because the truth is we don't really care what the magnetic field is on the outside. In fact, that's related to number 19. Compare the magnetic field inside the loop. I've drawn only 2 of the vectors, and I didn't draw them very well. They should be parallel. Compare that to outside the loop. I'm hoping you remember I took the magnetic field on the outside of the loop. What was the magnetic field basically on the outside of the loop? This is where you guys, yeah, nice, hit 0, thank you. So the magnet, that's your answer for number 19, by the way, it's 0. So the Amperian loop doesn't make sense to be in a circle in this case. The Amperian loop instead is going to be kind of like the picture I've drawn here. Do you see how it's kind of a square? But I want you to think about it. So what you're doing for this Ampere's law is you're integrating. They actually call it a line integral. You're going to be integrating all the way around this loop. So in other words, we're going to start at A. We're going to integrate from A to B. Then we're going to integrate from B to C. Then we're going to integrate from C to D. And then finally, we're going to integrate from D to A. First of all, when you integrate from C to D, how much magnetic field is there outside the coil? We just said is how much?
0.
It's 0. So really, when you integrate along this path up here, you're going to get 0. It drops out. The other thing is the B field has to point along the path, either along it or in the opposite direction. In this case, let's look at from D to C. Can you see the magnetic field points to the right, but the path is pointing upward? None of this magnetic field points in the direction I'm integrating. So therefore, when I integrate along this path, it's also 0. And then finally, when I integrate from D to A, the same idea. The magnetic field points to the right. I'm moving from D to A. I'm summing up all that B field that points in that direction, and none of it points in that direction. All points to the right. It doesn't point in this direction. It's unlike the picture that I showed before where we had one wire and we had a loop around the wire. The magnetic field always points in the same direction as the loop. This one's not. It's only pointing along the direction from A to B. So when I integrate, I'm really just taking and figuring out what the length of this is. All right, so by the way, here is Ampere's law. Kind of looks a little bit like Gauss's law. Not exactly though. So instead of a closed integral of E dot dA, it's closed integral of B dot dL, because we don't care about the area, we care about the length. And instead of being Q enclosed over epsilon naught, it's going to be mu naught times I enclosed. So it's a total amount of current that's enclosed. So number 20, the number of currents inside the Amperian loop. So I want you to look up here. Can you see that if I count up all these currents, I know you're thinking, well, it's just one current because it's just one wire, it's just looped around. You're right. But those currents create a magnetic field that adds together. And so really what I have to do is I have to figure out how many of them total there is. So down here in number 20, the number of current loops inside the Amperian loop is N. So if you look at the right-hand side of this equation here, the right-hand side,
Who's that?
I want the total current. So what do I have to multiply I by to get the total current?
Number of loops.
Exactly, yeah. So if I want to figure out that total and current, the total current, I total or I enclosed, that's going to be equal to the current through the wire times the number of loops. So in this case, they use a big N, so I'll use a big N. Okay, for number 21, assume the magnetic field in the, sometimes they call these slinky solenoids. So assume the magnetic field in the solenoid is B and the length from A to B is L. What is the integration from A to B? So if I'm integrating B dot DL, B is constant. So let's see, I don't know if I can write this or not. This is gonna be hard to do. So let's say, I'm gonna say this is the closed integral of B dot DL. That B is constant, so it's really gonna be B integral of DL. Well, when you go from A to B, if from A to B is L, when you integrate DL, what would that just simply be equal to? I'm not making any sense there. Okay, let me see if I can try again. So the B field is constant. Inside this coil, it's constant. So I was able to factor that out of the equation, out of this equation on the right hand or on the left hand side. Dang it. So I was able to factor out the B. So therefore, I'm really summing up DL, and I'm just doing it from A to B. I'm telling you the length from A to B is L. So if I were to integrate DL, what would I get?
L.
Yeah, I just get L, right? And so really, this is just simply on the left-hand side, I just simply get B times L. We've already talked about 22, 23. If I integrate from B to C, what would I get?
0.
0, nice. And from C to D, given that there's no magnetic field out there, what would it be?
0.
0 again. And then finally, where am I at? Oh, and then finally integrating all the way around, it's just simply going to be BL. So let me put that all the way down here again, BL. Okay, so on the left-hand side, I have BL, and on the right-hand side, that was this equation up here, I have, well, I forgot the mu naught, so I put equals mu naught, but then times I times N. And now if you were to solve that for B, do you get the exact same equation we found in the lab? Yes, yes, okay. I think I still have to give you the last 3 numbers, digits. So the last 3, and then we're almost done here, is 215, 215. Okay, so let me tell you then, oh, I also need you to type in your name, first name, last name for attendance purposes again in the chat. Again, the number was 215. So what I'd like to do is get your lab response. I'm hoping you have your paper version. If not, maybe, I don't know, you could download it somehow and put the answers. I'm hoping you could just take a picture of it or something and send it to me, or maybe you guys can figure out a way, I don't know. That way I can grade it.
We have it online, like if we fill it out, is that okay too or no?
It was kind of hard to hear you there, Mark. Can you say it again?
If we have it filled out, if we have our lab response done on the Google Doc.
It sounds like you're
On the computer.
You're kind of in an echo chamber. Can you get closer to the computer or something? Is anybody able to hear him? I don't know what he said.
He's asking if we can just do it on the shared document online.
I kind of want, thank you. I kind of want one copy from each person. So if you want to, I don't know, somehow work together on it, that's fine. But I think I want different. Yeah, okay.
Group FaceTime afterwards.
Okay, so we're not going to do the Ampere's Law worksheet. We'll just save that for next time. Now let me tell you about as far as doing the SWIC or not, who's excused. So I believe for sure, hold a second. I know for sure that these people for sure can be, come on. So Mark, Aiden, and Joe, assuming you typed your name in every time I asked you to, you don't have to worry about the SWIC. Although if you want to do it, you can. It's not that hard. Riley, if you're here, if you've also typed in your name all the times I've asked you to, you're excused. You don't have to do it. Matt.
Hey,
and Kevin-
Mr. Lenfestey.
Yep.
Josh and Matt and Rob helped me on that too.
Well, what I saw was I only saw that you had done it, edited it. So I will look again to see,
Okay.
you know, the times and everything. But again, it's not a penalty. It's not hard to do the SWIC. It'll probably take 5 minutes. Matt and Kevin, same thing. You guys are excused from it. You don't have to do it if you don't want to. Matthew, Miranda, Kylan, you guys are excused. Again, assuming you guys have typed in your name those times I asked. Michaela and Kenzie, you guys are excused, assuming you typed in your names. That doesn't mean these are the only people excused. I know some people sent me emails of stuff and I didn't have time to check. So I'll probably send you an email in a little bit, but the truth is it's not going to be hard to do that SWIC. So, I mean, it's simple stuff. So it's like questions that you saw on here. So anyway, so that's it for today. Please don't forget that we have another one of these meetings on Wednesday at 1:05. Okay. Okay. Thanks for bearing with me. That was a long meeting. All right. Goodbye.
FaceTime me, Mark.